Well, hello everybody. Welcome to another day of Math 300. Uh, so, last time what we talked about we were doing proofs by induction. And today what we're going to do is we're going to move on to relations. So a new topic. It gives us a new area of some more material to work with to talk about different types of proofs. And so what I want to start off with is just what is a relation. Well, what we'd say is that a relation on A, any set A, so it is a relation if it's a subset of A cross A. We could also say R is a relation from A to B if it's a subset of A cross B, but we're going to focus primarily on relations on one set A, so that is a subset of A squared. Therefore, what we do is we say that, okay, R is this subset of A squared, so if we take any element A comma B, or the ordered pair A, B, and R, we're going to say then that A is related to B through R, or we'll say that A R B. So a relation is a subset of A squared. I'm going to have all of my ordered pairs, and I'm going to say that A is related to B if A comma B is in my relation. So for an example of that, let's look at, oh, I went a little too far. I'm going to go back here. All right, so let's suppose A is just the set 1, 2, 3, 4. So we'll use a small set. So what we could say is one relation would be R is the set consisting of ordered pairs 1, 2, 1, 3, 2, 4, 2, 1, 3, 2. So we could say that 1 R2, 1 R3, 2 R4, 2 R1, and 3 R2. And notice that those are ordered pairs, so the direction does matter. So I could say 1R3, but I would not say 3R1 because the ordered pair 3, 1 is not in the set. So anything that's in the set, any ordered pair gives me a pair of related elements where the first is related to the second. Now, just like with any set, we don't have to define it by listing. We can define it by roles. So we could say S is the set of all X comma Y in A, cross A rather, such that X is less than or equal to A. So what would that look like? Well, 1, 1 would be in that set because 1 is less than or equal to 1. So would 1, 2, 1, 3, 1, 4. And so we could say 1 S2 because 1 is less than or equal to 2. Now, I'll go ahead and go up to the chalkboard for this one. But we could also talk about the intersection of those two relations. So I could say, when is X related to Y through both R and S, or what does R intersect S look like? And so if I find just the set R intersect S, I'm going to get the set, which is equal to, well, if we just look at our ordered pairs in R, that the first one is less than or equal to the second, we get 1, 2, 1, 3. What's the next one? 2, 4. But then if I write down 2, 1, 2 is bigger than 1, so that's not true. And 3, 2 is not in there. So if I find the elements which are in R and in S, it's going to be exactly these three ordered pairs. So we could say 1 is related to 2 through the intersection of the two relations. So not only can we have relations, we can also talk about intersections. Just like with sets, and we could also talk about unions or differences and kind of combine those into some type of relation. But here we're going to be doing intersections often enough that I wanted to look at those at least and say something like, okay, so 1, 2 is in R and S, therefore 1 is R and S related to 2. And so that's how we're going to be using these things. All right. Another relation here that I have is, let's suppose that A is equal to R. So A is R. So S is a subset of R cross R, where, I'll move my head, X is related to Y if Y is equal to X squared. What I wanted to know was, what would this relation look like? Well, we'd have ordered pairs where the first element can be anything, but the second element always has to be the first element squared. So we'd have 1, 1, 2, 4, 3, 9. We'd also have 1/2, 1/4 because I'm working in the real numbers. And actually notice that because A is just the real numbers, S is a subset of R squared. If you remember back to way in the beginning of the class when we were talking about describing sets, this is a subset of R squared, so we can describe the set graphically. So what I could do is plot out all the points are all the ordered pairs in the Cartesian plane that are in S. And if I do that, notice that I'm just going to end up with the parabola y equals x squared. So not only can we represent things by actually writing down all the elements, but we can also graphically represent them by drawing what they're going to look like. So I will refrain from actually drawing a parabola on the board because I know that you guys all know what it looks like. You could imagine seeing that up there. And each of those points then on that parabola would be in this relation S. And so we would say that x is related to y whenever y is equal to x squared. All right. Now, what we're going to do here is focus on special relations and different properties that they have. And a lot of what we're going to be doing is showing that relations that we define have distinct properties. One type of relation that we're really interested in are equivalence relations. And so an equivalence relation is a relation which satisfies the properties that if A is in S, A is related to S. So here I'm using the tilde here to denote related. That's pretty common for the equivalence. So we'd say A is equivalent to A. And so for a reflexive relation, A has to be equivalent to A. So just as a quick note, if we look back to R here, R would not be an equivalence because, for example, 1 is not related to 1 because we do not have the ordered pair 1, 1 here. Whereas if we look at S, 1 is less than or equal to 1, and 2 is less than or equal to 2, and 3 is less than or equal to 3, and 4 is less than or equal to 4, so S would indeed be a reflexive relation, whereas R wouldn't. Alright, let's go back to our definitions. The next thing we're going to want to look at is symmetric. So we would say a relation is symmetric if whenever A is related to B, then also B is related to A. So that is, if 1 is related to 2, 2 has to be related to 1. Or if I look at these as ordered pairs, whenever I have the ordered pair A, comma B, I also have the ordered pair B, comma A. So that will be symmetric. And a real quick look back, notice that R, to be symmetric, we say, well, we notice that 1 is related to 2, and 2 is related to 1 because both 1, 2, and 2, 1 are in there. But we noted earlier that 1 is related to 3, but 3 is not related to 1, so that is not a symmetric relation. The last relation we're going to look at is transitivity, where we'd say that a relation is transitive if whenever A is related to B and B is related to C, this implies that A is related to C. So that is, let's say 1 is related to 2 and 2 is related to 3, that implies 1 is related to 3. Now, if I have all three of those things, what I'm going to have is what I would call an equivalence relation. And why is that called an equivalence relation? Well, I'm going to actually check these against different things here. I'm going to start off actually with the third one I noted here was the equality. And so if we use equality and we run through these properties, if, say, on the set of real numbers, we define equals as a relation, we just think about, let's suppose I have a real number. Is any real number equal to itself? Well, 5 is equal to 5, 6 is equal to 6. Yes, that makes sense. So equality is reflexive. Also, equality, if A is equal to B, this implies that B is equal to A. So if I have that 5 is equal to, well, it's only equal to 5, so 5 is equal to 5. So if A is related to B, then B must be related to A, so equality is also symmetric. Furthermore, if A is equal to B and B is equal to C, we get, well, A and B are the same and B and C are the same, so therefore A and C have to be the same. So equality is an equivalence relation, and so an equivalence relation really is kind of a generalization of an equality relation. It defines some type of equality, but the equality need not be just they're exactly the same. We would say that they're the same with respect to this relation. And so that's where equivalence relations come from, are kind of generalizing equalities. Now, if I look at these other ones, let's say less than, let's determine is less than a equivalence relation. And so I have to say, is it reflexive? And so let's say on the real numbers anyway, is A less than A? So that's the question we're asking for reflexive. Notice that 5 is not less than 5, so this is not reflexive. And that's what our proof would look like, is we'd say it's not reflexive because I'd give an example, 5 is not less than 5. So it's not reflexive. Is it symmetric? So if 5 is, or if A is less than B, does this imply that B is less than A? Well, no, that's not true. In this case, because if 5 is less than 7, we do not get 7 is less than 5. So less than would not be reflexive. Would it be transitive though? So that is, if A is less than B and B is less than C, does that mean that A is less than C? And so here I'm just going to think about, okay, well, if I have a number that's less than another number, so 5 is less than 7 and 7 is less than 9, does it have to be the case that 5 is less than 9? Well, it works out for that one case, but in general, if A is less than B and B is less than C, then yes, A is less than C. And so this would be a transitive relation, but it would not be reflexive. It would not be reflexive, and it would not be symmetric. So this was symmetric. I didn't write in there. So less than is non-reflexive, non-symmetric, but it is transitive. All right. Now, I do want to look at less than or equal to. If I do less than or equal to, notice that, well, it is true that for any real number, it is less than or equal to itself because it is equal to itself. So less than or equal to would be a reflexive relation. It would also be transitive for the same reason less than was. So we would have reflexive and transitive. And would it be symmetric? Well, if A is less than or equal to B and B is B less than or equal to C? Well, notice that if this was the case, if A was less than or equal to B, is B less than or equal to A? If this was the case, A would be less than or equal to B, B would be less than or equal to A. So that would imply the only way that this could happen is if A was equal to B. So if A is not equal to B, this is not true. So 5 is less than or equal to 7, but 7 is not equal to less than or equal to 5. So this is not a symmetrical relation. And in fact, because the only way that I could have two things related in both directions, what I'm actually going to call this is an anti-symmetric relation. So here I have a reflexive, an anti-symmetric relation, and a transitive relation. And so in general, if I have a transitive anti-symmetric relation, I'm actually could call that a partial ordering. instead of just calling it an equivalence relation. So this would be a partial ordering instead of a equivalence relation. We're not going to prove things about partial orderings. I'm just mentioning it's a different type of relation that we may want to look at some point in time. So there are other relations that are important, other relations that are useful. It's just we're going to focus mostly on equivalence relations in this class because they're a nice part to start doing some proofs with. But I did want to do this one just to show you that. All right, so you guys have been pretty quiet. Do you have any questions so far? Is this making sense? Or do I need to go back over anything? All right, well, I'm going to assume it's all making sense then. So let's try another relation. Let's let P be any arbitrary point in the plane r squared. And if I pick any other points in r squared, x and y, I'm going to say that x is equivalent to y if the distance from x to P is equal to the distance from y to P. So that is, the distance from P to y and to x are the same. And what I want to do is to show that this is an equivalence relation. So I'm going to give you a second here and think about, okay, if I need to show this as equivalence, I have to show those three properties. So I have to show it's reflexive, symmetric, and transitive. So do I think it's each of those? So think, is this reflexive? All right, I'll let you think about that. Try to write down your answers, but then I will go up to the board in a minute here. All right, so for reflexive, I have to say, let x be a real number. I have to show, or let x be an r squared, because in this case, we're working in the Cartesian plane. I have to show that x is related to x. And notice that x is related to x, or x is related to y, if the distance from x to P is the same as the distance from y to P. So what I want to think about is the distance from x to P equal to the distance from x to P? Well, if I take a point P, say here, and I draw x, and I find that distance from x, well, that's exactly the same as the distance from x. So the distance from x to P is the distance from x to P. Hence, we get that x is, in this case, related to x. So I do get a reflexive relation. Symmetric. Suppose that x is related to y. What we want to show is that y is related to x. So what we get is that since x is related to y, the distance from x to P is equal to the distance from y to P. But notice that if the distance from x to P is the distance from y to P, then the distance from y to P would be the same as the distance from x to P. So that would be, there's some y over here. These two distances are the same. So I even draw the marks in there. Those are equivalent distances. And so if the distance from x to P is the distance from y to P, well, then the distance from y to P is the same as the distance from x to P. I can switch the order on the equality. So we do indeed get y is related to x. All right. Now if I think about transitive, what I'm going to do is let x be related to y and y be related to x. or z rather. I need a third one. So what I have to show now is that if x is related to y and y is related to z, that x is related to z. So what I have is I know there's a distance from x to p, and the distance from y to p has to be the same. Now also the distance from z to p has to be the same as y to p. So what I get is that if I draw this in, these two are the same. But now if I look at this, notice that if these two are the same and these two are the same, that implies that all three are the same. So that implies that the distance from x to p is this distance from z to p. So what it would say is then distance from x to p is equal to the distance from y to p, which is the same as the distance from z to p. Hence, the distance from z to p is the same as the distance from x to p, so x is indeed related to z. Therefore, this would be a transitive relation. So, this whole being the same distance from an arbitrary point would be an equivalence relation on r squared. Now, just as a further step, I could think about, well, if I have an arbitrary x here, can I find all the elements related to it? Well, all the elements related to it are all the ones equidistant from p. So if I draw all the points equidistant from p, what I'm going to get is just a circle with the radius, the distance from x to p. So if I want to find all the things that are equivalent to x, they're actually just going to be all the things on the circle. And if I want to find another point where, let's say this is w, I know the blue isn't turning on too well, but the idea is that all the things related to w are just going to be the circle centered at p with the radius wp. And so what I'm going to get is all of my, I'm going to call these equivalence classes. The class of all things equivalent to something is going to form, in this case, circles with center p. And so a lot of times we'll want to take that extra step to kind of visualize what those are going to look like. All right. Now, so I'm skipping ahead one just to talk about what I was just mentioning, is that we will actually define equivalence classes. So if we have an equivalence relation on a set S, then we're going to define the equivalence class as reusing those braces with an A inside it to mean the set of all x which are equivalent to x. So the subset of S is called the equivalence class of A. So all the things that are equivalent to A are indeed going to form this set, which we call an equivalence class. All right. Now, since we're talking about sets again, what I want to do is talk about another type of thing we can do with sets. And so I'm going to say a collection P of non-empty subsets of S. So I have a bunch of subsets of S. To put them together, and I'm going to call that collection of sets P. I'm going to say that that forms a partition of S, provided that S is the union of all the sets in P. So that is, S is the union of all of the sets in P. And if I have two sets, then the intersection is going to be empty. So whenever two sets in the partition are non-equal, they have to have no intersection. So let's actually look at what a partition would look like. Sorry. So if I go up to the board, let's just say the board is my set. So all the points on the board are my set. So the partition, the idea is that if I take all of my subsets, I'm going to get the whole board. So I can say this is one of my subsets. This is one of my subsets. This is one of my subsets. And so if I want to partition, what I have to do is I can't have any overlap. Sorry, I had to sneeze there. So what I want to say is I can't have any overlap, so I can't have sets that look like that. As notice there's overlap there, so that would not be a partition, so I can't have that picture. But I can have something that looks like that, because there is no overlap. Now the other thing is it has to make up the whole board, so if I continue to draw these things, let's just say I built a big square around the edge, then what I get is this set, this set, this set, this set, this set, and this set all together. The intersection of each of those is empty because none of them overlap. But if I look at all of these sets, which includes this big one out here, I get the entire board. So any way I break this down, as long as I don't overlap at all and I get the whole thing, that's going to become a partition of this set, which in this case is my board. If I want a partition of a set, say 1, 2, 3, so let's work with numbers. A partition would be something like this is the collection of sets, the set of sets. Let's say 1 and 2, 3. So I broke this into two sets, one consisting of the element 1 and one set consisting of 2, 3. So if I take the union of these, I get the whole thing. If I take the intersection of these, I get the empty set. So that indeed would be a partition. All right. So now why did I bring up partitions? I have a really long theorem here. I'm going to not read the whole thing to you, but I wanted to put it all in there precisely so that you can look at it if you need to. But the reason why I'm bringing up partitions is because there's a natural relation between relations and partitions. And what that is if I find an equivalence relation on a set S, then the set of equivalence classes will always form a partition. Also, if I have a partition, I can define a relation on S as A is equivalent to B if and only if they're in the same set within the partition, and that will always be an equivalence relation. That is, if I want to talk about equivalence relations, I can equivalently talk about partitions. And if I want to talk about partitions, I can equivalently talk about equivalence relations. So there's this one-to-one correspondence where if I can find one, I can find the other. Now, why is that so helpful? Well, anytime we can find the same thing by doing through different routes is going to be helpful in math. So if we want to know what all the equivalence classes are, that might be difficult, but finding all the partitions might be easy. So we can just find all the partitions and we get all the equivalence relations. Or if we want to find all the partitions, we can instead find all the equivalence relations. And so one of those might be easier than the other within some context. So having both of these available is nice to see. All right. So with that in mind, I want to look at an equivalence relation, and I want to talk about, okay, what is the partition it would form, and what would that look like? So one such relation that we've actually dealt with before is congruence mod n. And so I'm going to stick with congruence mod 5 for now, just to give a concrete example. But what I want to do is show that congruent mod 5 is indeed an equivalence relation. If I do that, I then want to find the equivalence classes and think about how that would partition the integers up. All right. So reflexive. What I need to show, or then, A is equivalent to A. So I have to show A is congruent to A mod 5, and I get to assume that A is an integer because I'm working on the set of integers. So I'm claiming that mod 5 is the equivalence relation on the set of integers. So I'm trying to set this up on my proof. I get to assume A is an integer. I have to say A is congruent to A mod 5. Well, If that seems clear, it is actually pretty obvious that if I divide by 5 and take the remainder, and I start with A, and I start with A, I'm going to get the same remainder. So that one you could technically just write down, but we could also work with, we also know that similarly by saying that A is related to A, what this is really saying is that 5 divides A minus A. So we could show that instead. And well, A minus A is equal to 0 times 5. So here we have a little bit more detailed proof of, well, I know A is congruent to B mod n if n divides B minus A. So this is just saying that 5 divides A minus A. But if I take A minus A, I get 0. 0 is 0 times 5, hence 5 divides 0. So 5 divides A minus A, hence A is related to A mod 5. So this is indeed a reflexive relation. And that again would work for any n, but I'm sticking with 5 just for a concrete example. All right, what's next? Oh, there's some other properties I have to prove, right? I think the next one is symmetric. So that is, let A be congruent to B mod 5. I have to show that B is congruent to A mod 5. All right. So if I use the same process I did up here, this is saying that 5 divides B minus A. And what I have to show is that 5 divides A minus B. All right. Well, clearly don't have enough room there. So I'm going to go and make myself some room. And so what I know is that 5 divides B minus A, and I have to show 5 divides A minus B. But this means B minus A is 5 times some integer. And I want to show that A minus B is 5 times some other integer. So now I'm ready. I can say A minus B is equal to, well, A minus B is actually just negative B minus A, which B minus A we already know is 5k1. So this is 5 times negative k1. But since k1's an integer, negative k1's an integer, so we can let k2 equal negative k1. And we get A minus B is 5 times k2, which is an integer. Hence, if A is congruent to B mod 5, B is also congruent to A mod 5. So we have a reflexive symmetric relation. And the last thing we need to do is prove transitivity. So for transitivity, we get to assume that A is congruent to B mod 5 and B is congruent to C mod 5. And I have to show that A is congruent to C mod 5. So how would I do that? Well, this means that 5 divides B minus A, and 5 divides C minus B. And to get, which this means that B minus A is equal to 5k1, and C minus B is 5k2. And what I have to show is that C minus A is 5k3. So I skipped a step here. I should say that 5 divides, on the other hand, what I have to show is that 5 divides C minus A. Says I have to show C minus A is 5 times some integer, and I'm up to k3. So again, I get to assume this. I have to show this. I wrote down by definition, that's what this means. That's what this means. And so by definition, I'm going to work my way back. And so now I have to get from here to here. And so what I'm going to do is just start with C minus A on the left, and I want to get the right out. Now, how am I going to do that? Is, well, if I look at this one, it's not abundantly clear how to do this. And so that's actually kind of the fun part here. But we're going to do something similar to what we've done before a couple times. Not that many, but a couple times. Is in order to get this to work out, I'm going to add a fancy looking 0. So that is, I'm going to rewrite this as C minus B plus B minus A. Now, why can I do that is, notice that if I subtract B and add B, I'm really just adding 0, so that doesn't change the problem at all. But the reason why I'm doing that is now I get a C minus B and a B minus A, and I know that both of those are already 5 times an integer. So I get this is 5k2 plus 5k1, which is equal to 5 times k2 plus k1. So after doing that and substituting my negative b and plus b, it works out that yes, this is divisible by 5, because I can let k3 be k2 plus k1. So congruent mod 5 will be an equivalence relation. And also, I'll let you guys kind of work on it, but if instead of using 5 the whole way, I had used n, just anywhere you see a 5, replace it with an n, you get that congruent mod n for any n is an equivalence relation on the set of integers. All right. So now the next part was I wanted to find the equivalence relation. So what I'm going to do is just start with a number. I like 0. So if I find the equivalence class of 0, what that means is find all the things that are equivalent to A. Oh no, my board is falling down. Hey, I think I got it back on, but not really. There we go. All right. Sometimes I lean on the board and that happens. Back to the problem at hand. If I want to find the equivalence class of 0, I want to find all the things that are equivalent to it. And what I would say is that A is equivalent to 0, or A is related to B if A is equivalent to 0 mod 5. So I want to think about what are all of the things that are equivalent to 0 mod 5. What that means is if I divide by 5, I get a remainder of 0. So one of those things is 0. Another thing would be 5, 10, 15, 20. And I can also go negative 5, negative 10 in both directions. And so what I'm going to get is the equivalence class of 0 is just all the things that are divisible by 5. If you guys don't see that, let me know. Make a comment. I'm having to go back over it. But I'm trying to find all the things that are related to 0 mod 5. So that just ends up being all the things that are divisible by 5. To continue, I'm just going to move on and say let's go from 0 to 1. So all the things that are related to 1 mod 5, so this is the set of all A such that A is equivalent to 1 mod 5. So I can actually explicitly write that out this time. So it's all A, I should say A and Z, such that A is equivalent to 1 mod 5. But if I want to list those out, 1 is equivalent to 1 mod 5, so is 6, because if I divide by 5 and take the remainder, I get 1. 11, 16, 21, and then negative 4, negative 9, negative 13. And so this would continue in every direction. And so these are all the things that I can write as 5 times some number plus 1. So these are all the things of the form 5k plus 1, such that k is in Z. Now, if I just follow that same thing, what I'm going to get is the equivalence class of 2 is all the things of the form 5k plus 2, such that k is in Z, or all the things that are congruent to 2 mod 5. And so I'm going to get 2, 7, 12, 17, negative 3, and I can go off in both directions, adding 5 each time. So I'm going to get infinitely many elements. If I write 3, I'm going to get 3, 8, -2, -7, 13. And then if I write 4, I get 4, 9, 14, 19, -1, -6. And so I can go off in both directions there. So what I'm trying to point out is so far, if I look at each of these, notice that if I look at 0 and 1, is there any overlap? Is there anything in here that is also in here? Or is there anything in here that is also in here? Or anything in here that is also in here? Or any combination of these? Well, if I look at all of these sets so far, and I try to find the intersection, well, the intersection of any of these two sets at a time is just going to be the empty set. There is nothing in common between any of these sets. Now, if I go on to the next one and I say 5, notice that the equivalence class of 5 is just all the things that are congruent to 5 mod 10. So that would be 5, 10, 15, 20, also 0, -5, -10. So if I do that, I actually just get the same thing as the equivalence class at 0. So if I find this, this is just the same as this. So these are actually the same sets. If I continue and find 6, notice that 6 is congruent to 1 mod 5. So these two actually become the same. And in general, what's going to happen is if I take any other integer, that integer is going to be congruent to either 0, 1, 2, 3, 4 mod 5. Therefore, its equivalence class will be one of these. So if I wanted to find all the equivalence classes, what I can do is just say all the equivalence classes will be equal to either the equivalence of 0, the equivalence class of 1, 2, 3, or 4. So we could say these are all of the equivalence classes. Now I've already pointed out that the intersection is empty, but if we take the union of each of these, well, since every integer is congruent to one of these mod 5, that means that the union of each of these is all of the integers. Hence, the intersection of any of these two is empty, and the union is the whole thing. So what I'm trying to point out here is that this set of equivalence relations is indeed a partition on the set of numbers, a set of integers, sorry. So that is, the intersection is empty and the union is all integers, so therefore this is a partition. So we started off with an equivalence relation, found the equivalence classes, and we got a partition. So that's that's a concrete example of what I was talking about the relation between those two. All right. Let's see. Instead of working with a concrete example, I actually want to go back and say, in general, why is it the case that an equivalence relation will always give me a partition, and a partition will always give me an equivalence relation? So let's suppose that tilde is an equivalence relation. What I want to show is that all of the equivalence classes, so if I let P be the set of X, such that X is in, so an equivalence class on A. If I let P be the set of all equivalence classes such that X is in A, I'm going to claim that this is a partition. So now, actually, I'm going to go back on my PowerPoint. I want to give you a specific example, but now I'm going to look at the general case. So I want to show this big, long theorem. So if I have an equivalence relation, I want to show that the equivalence classes will form a partition. So what do I have to show is that if I take any of these sets, that their intersection is empty or they're the same set. So that is, what I have to show is that if I take A and B, one of two things happens, is either A is equal to B, or the intersection of A and B is empty. All right. And I also have to show the union of all of the equivalence classes is equal to A. So these are the two things I have to show that this is a partition. I'm going to start with this one because it's actually the easier one, and then I'll get to this one. So let's make some room. I want to show the union of all of these is equal to A. So what I have to do is, first off, I want to point out that in order to show the equal, I show this is a subset of this, and I have to show this is a subset of this. Notice that A is a subset of A for all A and A. Why is that the case? Is because the equivalence class of A is defined as elements in A which are equivalent to A. Therefore, each of these equivalence classes is a subset of A. So when I take the union of all of these on A, notice that each one of these is a subset of A. So if I take the union of all of them, that again is going to be a subset of A. So now I could go through a little bit more formally, but the idea is that if I take the union of sets that are a subset of some set, I'm still contained within that set because all the elements in the union are in one of these sets. Therefore, they're all in A. So therefore, this is a subset of this, follows fairly quickly. On the other hand, to show that A is a subset of this, what I have to do is I actually have to say, okay, let A be an A. Then I have to show that A is in one of these. Then A is in, well, what I want to point out is that because tilde is an equivalence, I know that A is related to A. Hence, A is in the equivalence class of A. That is, it's in the things that are equivalent to A. Hence, this is contained, or a subset of the union of all A and A of the equivalence classes. Therefore, A is in this equivalence classes is in the union of all of these. I should probably use a different letter here, so I'm going to do that. Therefore, this is, or A is a subset of this. This is a subset of A, so they are equal. So if I take all the equivalence classes and take the union, I do indeed get the entire set because everything is equivalent to something, namely itself. All right. Now I have to show that the intersection of any two is either empty or they're the same thing. So what I'm going to do is say, suppose we have A and B and A. If the intersection is empty, then we have the theorem because the intersection is empty. Right? That's what we wanted, is either it's empty or they're equal. So let's suppose they're empty. Well, then we're good. So otherwise, let's suppose that the intersection is non-empty. So the intersection is either empty or non-empty. If it's empty, we're good, because that's one of the things that we're okay with. The other thing we need to show is that if it's not empty, well, then what we need here is to show that they have to be the same thing, because that's what's required of a partition. So if it's empty, we're fine, but if it's non-empty, we have to show then A is equal to B. So that's our goal here. All right, I'm going to need more room for that. But I wanted to point out that, okay, we get to assume that A intersect B is non-empty. Hence, there exists a C such that C is in A intersect B. So there is some element in there. But if C is in the relation of, or the equivalent set of A, that means A is equivalent to C. And if C is in the equivalence relation on B, that means that C is equivalent to B. But we know that this is an equivalence relation, so A is related to C and C is related to B, so that means that A is equivalent to B. Since A is equivalent to B, that means that all the things equivalent to A are also equivalent to B, and all the things equivalent to B are also equivalent to A. Hence, all of these things are actually the same, so the equivalence class on A is equal to the equivalence class on B, because all the things equivalent to A are also equivalent to B by transitivity, and all the things equivalent to B are also equivalent to A by transitivity. So therefore, that was saying this is a subset of this is a subset of this, so they then become equal, and we get out exactly what we wanted, is that if we look at equivalence classes, either their intersection is empty, or they're the same equivalence class. So every equivalence relation does indeed give us a partition when we look at the equivalence classes. All right. I know I'm going a little bit over, but I do want to finish this proof. So I'm going to say let P be a partition what I can then show is that if I let A be related to B, if A and B, well, let's say P is the partition, and it consists of all the sets of A sub I such that I is an I, and I'm going to let A be equivalent to B if A and B are in the same A sub I. Then I claim that that's going to be an equivalence relation. So this is a partition. These are all, the intersections are empty, and then the union is the whole thing. I want to show that this is then an equivalence relation. So I'm going to just start off and say, is it reflexive? Well, reflexive means that A is related to A. So to show that, we'll notice that we're really just saying that A is in the same A sub I as A. Well, if A is in the set A sub I, because it has to be in some set, it's in the same one as it's in. Therefore, yes, A has to be related to A. If I try symmetric, well, if A and B are in the same set, then B and A are in the same set. Therefore, it is symmetric. And if A and B are in the same set, and B and C are in the same set, so this is transitive, notice that I have then, here's one of the sets is A and B, and then I also have a set B and C, because B and C have to be in the same set. But notice now there's an intersection between these two sets, so because it's a partition, those have to be the same sets. So that means that A and B have to be in one set and B and C have to be in the same set. Therefore, A and C are in the same set. So therefore, this will indeed be a transitive relation. So if I define from a partition, this is my relation, every partition will indeed give an equivalence relation on the set A. Therefore, again, we have a one-to-one correspondence between these. So whenever I find an equivalence relation, I can find a partition, and whenever I find a partition, I can find an equivalence relation. So just to recap kind of what we've done today is we talked about relations. We defined them as a subset of the original set squared. And we talked about the ordered pairs, and we said, well, then A is related to B if the ordered pair AB is in there. Then we talked about different properties they may have, such as reflexivity, symmetric, or transitive, or even antisymmetric we mentioned. And then we went through and we proved that these different relations had these properties. And so we're going to spend some more time with relations in general, talking about what are different properties they might have, what are different things we can prove about them. All right. Thank you for joining me today, and thank you for staying a little bit late. I will see you guys on Friday.